Thank you for your time as we go over another practice final here for physics. My best advice for you on this exam is to take your time. Make sure you read over everything very carefully. Have time to double check your work. Um, I will try to write this exam so that 2 hours allows you to work at a comfortable pace, allows you to finish everything, and does allow you to kind of double check everything. So you will start with some multiple choice that will be similar to these practice finals. Keep in mind, our course could have been called Physics with Constant Acceleration. So a lot of the motion that we looked at this semester is acceleration due to gravity. And we don't change the acceleration due to the Earth's gravity just by throwing a ball or sliding a block or rolling marbles or launching marbles or anything like that. Now, when you're given these little small multiple choice problems, um, that are story problems, the equation will be listed. So like this number 2, it would say acceleration equals delta V over t to help you with that. A flat line on a position time graph, just think about that as something that's not moving. So if it's not moving, the velocity is 0. Now, this idea that unbalanced forces will result in a changing velocity, that does come back to understanding our motion graphs. So I think of this motion graph here, like our first day of school. So those little cars we had out in the hallway, we did a hand-drawn graph where our position would change at a very steady manner. The slope of that line is a constant positive slope. So our velocity is a constant positive velocity. The slope of that line is 0. So our acceleration is 0. Now, if something is changing its velocity, that's where we get a curve on our position time graph. For physics, a good way to think of a curve is a changing slope. How does this slope here changing? That slope is steadily increasing. Think of the lines tangent to the curve. How would their slope change? Those lines tangent to the curve get their slope becomes more positive. Our velocity becomes more positive. This line, any point you want to pick, has a constant positive slope. So our acceleration would be a constant positive value. But to get things to move, when you unbalance those forces, you do change their motion. You do change how their velocity moves. You could change their acceleration, but the acceleration could also stay constant. So the one answer that kind of fits all of those for unbalanced forces would be a changing velocity. Number 5 is just velocity equals distance over time. And it's really asking you for what are the correct units of time to answer that. If you saw a question like 6, it would say acceleration equals delta V over t and ask you to solve for that delta V. Now remember, when you solve for delta V and your object starts from rest, delta V does equal that final velocity that they reach. A question like 7, it's the only statement that matters is this: down is the positive vector, down is the positive direction. That's the only statement that really matters in this. You could launch a marble up in the air, throw a baseball. You're not going to change the acceleration when that happens. So we've been plugging and chugging. Think of all of our free fall problems. We would plug in 10 for our acceleration due to gravity. And when you do that, you are assuming that gravity is, when you plug in positive 10, that means gravity is always acting in the down direction. So that would make that acceleration also a positive vector. So the whole key out of this statement is just what direction is positive. If the positive direction that we've defined is the same way that gravity will function, then you get a positive value for your acceleration. Being in orbit, number 8 there, being in orbit, you are very much under the influence of the Earth's gravity. Yeah, now kind of back to this idea of if acceleration has a number. So like a lot of times we would plug in, positive 10 for our acceleration due to gravity. Well, if you multiply that by the mass, that would give you force due to gravity. That would give you the weight. So the acceleration that you plug in the A that you plug in, multiply it by the mass of that object, that will tell you how much force is acting on it, or what that sum, that's what this sigma is, that's the sum of the forces would be. Now, along the same lines, if it's a constant velocity, if your acceleration is zero, if A is zero, then the sum of the forces acting on the object are zero, equals zero, and that's what we say those forces acting on it are balanced. So balanced forces will result in not changing the motion, or just keeping something moving at a constant velocity. If you do get a value for those forces, or if you do have a value for your acceleration, that means your object is accelerating. You are changing its motion there. So, okay. Understand that complementary angles will land in the same distance, the same dx. So range is really horizontal distance. The time something spends in the air is a function of the height that it reaches. So d would be launched to the highest height, the most altitude, so that also would be in the air for the most time. 11 and 12, yeah, that just goes back to this. If you increase the force, you're going to increase the acceleration. If you increase the force and the mass, then that acceleration value won't change. So that's what's going on there with 11 and 12. 13's just asking if this thing is going to move horizontally, this will have the greater force applied horizontally. Which one has the greater FAX? Well, it's going to be A. 14, now which one? Now normal force, my favorite definition of the normal force is what would a scale read? Or maybe think of it, what's that pressure between the two surfaces? So if you do pull up a little bit, pulling up a little bit is going to take some of that pressure off between the two. So A would have more pressure, a greater normal force. Remember, balanced forces result in not changing the motion, so keeping that velocity constant. Unbalancing those forces, things fall, things tip over, things accelerate. You do change the velocity of things when the net force acting on them does not equal zero. Okay. Please, force due to gravity is weight. Force due to gravity is weight. Mass, it's really a measure of the amount of matter in a substance. 19 is just asking you this direct proportion. That would mean you're changing the numerator. So if you increase the mass, you increase the force due to gravity. So if they both increase, that is a direct proportion, a direct relationship. When you add weight to something, you don't change the mu value. All right, so mu, think of it as force friction divided by force normal. That ratio stays constant as you add weight to things. Units, hopefully that's very straightforward. The biggest key on this is weight is force due to gravity. So if weight is force, force is force. Y over x, just think, and I'll pick some graphs that we've made, but just think y divided by x. What does that equal? Change in velocity over change in time. Change in position over change in time. F divided by A. F divided by A. F divided by A is going to equal mass. Force friction divided by the normal force, that's mu. That it stays constant for any two surfaces, any two materials. These, I think we're getting pretty good at these, but this is just F equals ma. So if I'm asking you to solve for A, it's force divided by mass. F equals ma, so it's mass multiplied by acceleration. Mass would be F over A, so that would be force divided by acceleration. And then weight and force are the same. The reason this is key is as we start second semester and talk about things like momentum and torque and energy and power, this simple relationship here allows us to define those pretty easily. Motion graphs, we've done a lot of this in class. My best advice for you on this is think in terms of slope. Think in terms of slope. So like not moving the same position all the time. That is a zero slope. That is a zero velocity. That is a zero slope. That is a zero acceleration. Now, constant velocity, this would be a positive slope that's constant. Positive velocity that stays constant. This slope is zero, so my acceleration is zero. You can move with zero acceleration. Free fall, think of the big blue marble. But this curve, the slope of this curve steadily increases, so my velocity steadily increases. This slope is constant, but it's positive. So that slope stays the same everywhere. So my acceleration stays the same the whole time. This last one is probably the trickiest one. An increasing velocity means the slope of your velocity line is positive. Decreasing speed indicates that the velocity approaches zero. So the only way to draw a positive slope on my velocity graph that approaches zero is like this. So it starts with a negative velocity and it approaches zero. That means my curve on the position time graph, it starts with a negative slope and finishes with a zero slope. Negative velocity, negative slope. Zero velocity, zero slope. Now this line here, that line is a positive slope. So my acceleration is a positive value that doesn't change. Okay, looking at a velocity versus time graph. Take a deep breath, get your bearings. Initial velocity, just look at time zero. So this one is a 0, 0. At 3 seconds, now I didn't really label it, but I was hoping maybe if you knew those 2 points and the slope, you could figure it out. But yeah, at 3 seconds, the velocity would be 4. So at 3 seconds, the velocity is 4. When is the velocity constant? Right here. That's where it stays the same. When is the slope negative? Right here. All right. Go back to here. Constant. When is the slope 0? Right there. If that makes sense. All right. So then E is asking you for the slope between 0 and 2 seconds. Rise over run. Just count it out. Just be simple. So it goes up 6 over 2. It goes up 6 meters per second in 2 seconds. That is an acceleration of 3. Now to figure out the distance, this question F is kind of tricky. Couple ways to do it. A lot of students like the area method, and it was a little confusing for some to figure out how do I draw the rectangles and the triangles. I divided it up this way. So I got a rectangle here. It's 2 over up 6. I got a triangle. I got a triangle here, which is up 4 and over 2. And then I got this rectangle here that has a base of 4 and a height of 2. So I find the area, and that adds up to 18. And the area on a velocity time graph does give us the distance, or really the displacement of that object. You could use the distance formula. The thing is, you just have to use all those slopes, all of those values of acceleration. So for the first 2 seconds, the slope was 3. So that's the acceleration. For the next 2 seconds, the slope was negative 2. Now be careful, you also began at a velocity of 6 for that interval. So make sure you incorporate that initial velocity for that interval. And then finally, the last piece where it was constant velocity, the slope was 0. So there's no acceleration there, but you did begin at a velocity of 2, and it stayed that entire velocity. So it was 2 and 2. So the velocity The initial velocity was 2. So you could get the same answer. It's a great way to kind of double check yourself. Use distance formula, get an answer. Use the area method, get an answer. All right, now I'm hoping when I give you a story problem with an animal running, you can make your own graph. All right, so I don't know what animal it would be, but it's going to reach a certain speed in a certain amount of time. And then it's going to maintain or hold that speed for some amount of time. And then that total time, it's going to ask you how far do they run. I think the easiest way is to set up a graph. It's going to be a velocity versus time graph. In 5 seconds, it got up to a velocity of 16 meters per second. And then it would hold that speed. So for 10 more seconds, 10 additional seconds, it will hold that speed. So at 15, the same speed. So you got 0, 0, 5, 16, 15, 16. You can connect those lines, connect those points. And then that's a simple one to find the area for. So you got a triangle there, a rectangle there, find the area. And the rule is the area between your line and the x-axis. You also could use distance formula. So remember, your slope is what provides the acceleration. So the slope of the first piece would be 16 over 5, or 3.2. The slope of the second piece is 0, but remember it does start at a velocity of 16. So if you got two different values for acceleration, use the distance formula 2 separate occasions, 2 separate times, and just make sure you incorporate the time intervals associated with each piece. But that's once again a great way to double check. The area or the distance formula should give you the same answers, the same results. Okay, now moving right along. Yes, the force problem. Now, when you see this, it will have the drawing for you. And I will break it up into steps for you like that. So hopefully these kind of make sense. Just looking at our most recent quiz, people have done well. When you see the angle, remember you're going to have to, that hypotenuse is your applied force. And so your FAX and FAY force vectors are really what you use to solve the problem. But yeah, first step is figure out the weight. So 22 kilograms will weigh 220 newtons. Please remember to subtract how much you pull up to figure out that normal force. All right, it doesn't equal the weight when you're pulling up a little bit. So I pulled up with like 25 newtons of force. So I got to take that off of the weight when I find the normal force. The significance of the normal force is you multiply that by mu and you get the frictional force. To add or sum those forces, just look at your picture. So I got 54 newtons pulling horizontally. I got friction pulling back with 9. So the difference between those, you're adding a negative. I think of it as just subtraction, but that's how you sum the horizontal forces. Take your applied horizontal force, subtract friction, and that's just F equals ma. So once you get your net force, divide it through by the mass, and that gives you the acceleration. If you know the acceleration, this is probably an easier way to look at it. Acceleration is delta V over t. So if you know acceleration, you can figure out that velocity at any moment. When it starts from rest, your final velocity equals your delta V. You can use acceleration to also figure out distances. So hopefully, yeah, just remember when you're plugging in A, use the acceleration that you found. Now, really, we have enough there to make a graph, too. I mean, this thing moved for 5 seconds. It got up to a velocity of about 10 in those 5 seconds. So here's my graph. It took 5 seconds. It got up to a velocity of about 10. And that does tell me how far it goes. So the area does in fact equal the distance. Woohoo! All right. How How much time does it take? So it's 2 kilograms doesn't matter. All right, and that's the whole thing. When we kind of looked at free fall problems, we did not consider the weight or the mass of the object. All right. If we consider friction and wind, it starts to matter, but really for our free fall problems that we're doing, we are going to ignore the effects of friction and wind and air for free fall for now. So just plug in your distance, solve for time. It really is that easy. Take your time. Don't forget the square on the time. So the last step is to divide that through. 29, now this is really a projectile problem where you're starting it at the peak. So it doesn't have to climb to the peak like a marble would. This is starting at the peak. It's going to be kicked or launched totally horizontally. So the way you do this is you use the height to figure out the time. So just how you're really solving that as free fall. Plug in your distance, get an answer for now. The weird thing is the time it takes to just fall from there. As long as you didn't give it any up or down thrust and just pushed it totally horizontally, the time it would take to land in the basket is the same as the time it would take to fall. So if you know the time and you know the horizontal distance, you can get horizontal velocities. Really, horizontal velocities, we say, are not affected by gravity. Projectile problems. Now, what I will do is I will tell you the steps too. So hopefully that I want you to do well on these. But I'll say, find Vx and Vy for step 1. So you can use cosine equals adjacent over hypotenuse to get Vx. Use sine, that should say sine to get Vy, sine. And those become the numbers you use. It's Vy that we use for step 2. Now remember, technically really what we're doing in step 2 is you're finding the time it takes to go from the peak to the surface. So this time really gets us from here to there. When you double the time, that's how you can get the total time. And then that's what you want to use to get total distance. Now, when we go to find height, though, how high up in the air did it go? Once again, technically, really what you're doing is solving for the height it falls, but that's going to equal the height it climbs to. But when you find height, just use the time that we found. Don't double it or anything like that. So this time is what you use. Yeah, 31. 31 is just careful reading, so you can get average velocities. When there's constant acceleration by taking VI plus VF over 2. It's just averaging 2 numbers is all that is. The acceleration is your difference in the velocity, your change in velocity divided by time. Now the distance, you got two options here to find the distance. You can use our distance formula. Just remember it did have an initial velocity, so it wasn't starting from rest. It was moving when it crossed the reference point. So be careful. Now the other way, remember, if you know the average velocity, that's going to equal distance over time. So we could use that average velocity to get the distance as well. So 2 ways to get the same answer on that. These hang time problems, so initial velocity for someone that jumps, technically really what we're doing is we're saying you jump this high and then you fall from that height. So we're going to make our initial velocity 0, and then the speed or the velocity you would hit the ground with actually equals the speed you would need to leave or to launch with to get to that same height. So these hang time problems, just like a level surface launch, it's all symmetrical. So use the height you fall from to get time. Once you got the time, plug it in. We can use our acceleration due to gravity to figure out our delta V. But once again, that speed that you would hit the ground with, that final velocity, that does equal the velocity you would launch with or leave the ground with to get to that height. Conversions, the key on these is just make it all 1 unit at a time. So 7 minutes
is 420 seconds, plus 10 is 430 seconds. So you go 1,600 meters, make that all 1 unit of time. That's the whole key. And then it's just drop the meters down, change it to miles. Move the seconds up and change them to hours. And then that's how you can do the conversion. But the whole key is just write down your distance over time in meters per second, but just write down your total time in seconds. These baby crawling ones, hopefully these are easy from what we've been doing. But yeah, distance is just what it means. I walked, or the baby crawled 12 meters and another 12 meters. So it went a distance of 24 meters. The displacement is just on a direct path from start to finish. So technically they were only displaced, that's the hypotenuse here. And then technically that would be their velocity. Alrighty. 2 lab cards. A couple things. You can ignore the negative for the way we're solving it. I just put that in to remind you it's moving in this opposite direction. But really this way I've kind of shown you to solve them, you can ignore that negative. The whole key is to take cart 1 and say its velocity is distance over time. That's all I can do. Now cart 2, I know its velocity, I can't say it moves the same distance, but I can say it moves 20 meters minus the distance that car 1 traveled. But the time, I can use the same t because it is the same. So I move this t over, and then I substitute that in for d. So right here, instead of writing d, I write 0.12t. And then what that does is that gives me this expression that allows me to solve for time. But really the shortcut, and a lot of students use this, the shortcut, if you look at this, that 0.42, think of both of those velocities added together. Once again, I'll make that positive for you on the final. But a good way to think of it is their velocities added together, multiplied by the time, will equal or cover that whole distance together. So yeah, that is a shortcut. Add their velocities, that's going to be multiplied by time, and that will equal the total distance that they cover. And then once you know the time, then you can substitute that in for each individual velocity to get the total to get the distance each car moves. A good way to check yourself is the distance should add to the total distance. Deep breath, deep breath. And you see this position versus time, just think about, okay, I'm starting at a 6 meter mark. I'm sitting still, sitting still. Then I get up and start moving. Now I'm going to move away and move another 6 meters out to the 12 meter mark. So the slope at the beginning is 0. Hopefully you see that as a 0 slope, 0 velocity. For the second piece, rise over run, I go up 6 over 4. Up 6 over 4. Think about that. Now to get the overall average velocity, you can't just average these two numbers. And the reason is because the first velocity you found is for 3 seconds. The second velocity is for 4 seconds. So they're not equal parts of the journey, so I can't just average those two numbers. So to get the overall average velocity, it is the total displacement over the total time. And in this case, the displacement and the distance are the same number. And that's because this thing never changed direction. So in this case, since I never changed direction, speed and velocity do have the same meaning. Okay, now this one, think about it. It's velocity versus time. So take a deep breath. It starts at a velocity of 2. It slows down, slows down, slows down, slows down, slows down, stops. And then it starts speeding back up, but it's just negative. But if you look at this, this is all one line. This would be a good example of something going up and down a ramp, where it would stop when it gets to the top of the hill and then start rolling back down the hill and pick up speed as it did that. So I'm hoping you can kind of get your bearings looking at that. So I start at a velocity of 2. I get to a velocity of 0 at 3 seconds. And then at the end, its velocity is like negative 2 2 2/3 or so. So, but if you look at this, it's all one line, so it should all have the same slope. And in fact, it does. If it all has the same slope, it has the same acceleration. So you can plug that in for A. Now be careful, if it's negative, you got to take that into account. That's really what, the importance of the vectors are, I guess. So yeah, it's slowing down, or that at least at first it is. But anyway, that value of the acceleration, if it's negative, make sure you plug it in as negative. There was an initial velocity, so be careful. It wasn't starting from 0. It wasn't starting from rest. So there was an initial velocity to consider. Make sure you consider the negative, and then you can get that answer. Now some students will draw triangles. But remember, the rule is the area shortcut is for the area between the line and the x-axis. This would be considered like a positive area or positive displacement. And this triangle here below would be considered a negative area or a negative displacement. So you could find the area of both of those triangles. One would be negative and one would be positive, but you still would arrive at that same answer. Anyway, I hope that helped maybe a little bit. Once again, I really appreciate your time. Physics is fun. Finals are fun if you're prepared. But really, overall, school's a lot of fun.
Why do you teach?
Well, I've always enjoyed school. I like learning new things, whether it's about our curriculum, about the material and teaching. I also like learning new things about people. And so teaching is definitely a job where you interact with people, and I learn something every day.